Welcome to Homework Lib.
This is chapter 35, problem number 40. We have two glass strips. In between them we have jelly. One thing we're given is n jelly is greater than n glass. And well, from what's observed from outside is lambda equals 525 nanometer fringes, dark fringes, so distractive interference there. And we are given the thickness of the metal foil is 0.015 millimeters, and the length of the glass strip is 8 centimeters. And we're also given the number of fringes, 10 fringes per 6.33 millimeters. So this is basically 1 over delta x that is given to us. So from here, we can actually calculate delta x, meaning the distance between two adjacent fringes is going to be 0.633 millimeters. So this is also given to us. Now let's look at what's going on at the interface of glass jelly and jelly glass. So when the light strikes this interface, it's going to reflect out of phase, right? A pi, because the index of refraction of glass is less than jellies. However, it's not the case at the second interface. So the overall phase change is going to be pi. And since we're talking about the destructive interference, then for the thickness at any point is going to be m lambda over index of refraction of jelly, right? So let's try and derive the distance between the adjacent fringes in terms of this thickness. So if this is the angle theta at any point, let's do the dotted line here so that we're not confused. Let's call this the thickness, and then let's call this as a function of x. As a function of x, tangent theta would give us t over x, right? So from this equation, thickness equals to x times tangent theta. So if we put this information in the equation here, twice x tangent theta equals n lambda over n jelly. If we isolate x out of this equation by dividing both sides by 2 tangent 1 over 2 tangent theta, then we have for x is n lambda over 2 tangent theta and jelly. Now let's write this in terms of indexes, right? xm then would be m lambda over 2 tangent theta and jelly, and xm plus 1, the adjacent, would be m plus 1 lambda over 2 tangent theta and j. Now we're trying to go to delta x, which is this minus this. Let's do it on the next page. So xm plus 1 minus xm would give us delta x. That would also give us lambda over 2 tangent theta and jelly, m plus 1 minus m, right? So then we have lambda over 2 tangent theta and jelly. Again, look at this equation. Delta x is given, lambda is given. We know what tangent theta is. Let's reinforce that. From the figure, the first page, tangent theta would be also this number, the thickness of the foil, divided by the thickness of the glass slab, right? So it's going to be 0.015 times 10 to the power of negative 3 meters divided by 8 times 10 to the power of negative 2 meters. Let's keep it on the side. We'll plug it in when the time is right. Meaning when we isolate n sub j with the index of refraction of jelly, because that's what is asked from us. So then lambda over 2 tangent theta, right? Multiply both sides by nj and divide both sides by delta x. So we're going to have lambda over 2 tangent theta delta x for our index of refraction of the jelly. Let's plug in the numerical values. 9 meters divided by twice the 0.015 times 10 to the power of negative 3 meters divided by 8 times 10 to the power of negative 2 meters times delta x. We had calculated it to be 0.633 times 10 to the power negative 3 meters. So when we plug everything here, we find the index of refraction of Joe to be 2.21.